Okay, thank you, George, for the invitation, and I'm very glad to be here virtually at least. So yeah, today I'm going to talk about the joint work with Erwan Rousseau, Georges Vittorio Pereira, and Frédéric Touzet about the symmetries of foliations, and more specifically about the symmetries of transversely projective foliations. So the setup is the usual one. We take a smooth complex projective variety and a foliation on X, which could be possibly singular. So we look at symmetries of foliation, meaning that we look at automorphisms or birational transformations which fix the foliation. So in this case, F star F is clear. To define the pullback foliation, we can just look at F as a subsheaf of the tangent sheaf. In this case, the pullback is defined in a usual way. While in the birational transformation, we need to take a double dual in order for this to have the properties of a foliation. So the question we want to ask broadly is how complicated can the action of this group of birational transformations be? So first, what do we mean by complicated? Well, the first thing to check is whether this group is finite or not. So we would like to give some condition under which this group Bir X of F is finite. Let me point out directly that the fact of having a lot of birational transformation in a complex in a projective variety is kind of strange. So for example, if X is of general type, then the group of birational transformations of X, even without the presence of an invariant foliation, is already finite. So somehow we'll look at special kinds of varieties already if we ask ourselves this kind of questions. So an intermediate situation, so it's clear that if this group is finite, then we will consider it very simple. An intermediate situation is can be found by looking at the action, instead of the action of this group on the whole variety, we can look at its action on the space of leaves. So this space of leaves, we can define it by considering an equivalence relationship of points on X, saying that 2 points are equivalent if they lie on the same leaf. We find out that this space is usually quite messy, so nearby points are not separated. It's usually best not to speak about this space of leaves at all. But the point I want to make is that looking at the action on the space of leaves just means looking at how an element, for example, of Bir XF permutes the leaves of F. So we defined Bir X of F as the transformations which preserve F, meaning that at least where F is defined and locally biregular, a leaf is moved to another leaf, but maybe it is exactly another leaf and not the same leaf. So we'll say that the action on the space of leaves is finite if there is a finite index subgroup of Bir XF which fixes every leaf. And in this case, we say that the action is transversely finite. So we would like to find conditions under which Bir X is finite, or at least transversely finite. So some previous results, Brunella proved that for algebraic foliations of P2, there is no non-elementary polynomial automorphism which fixes them. Kanta and Favre classified in a quite complete way the foliations on surfaces which are invariant by infinite groups of birational transformations. And Pereira and Sanchez proved that foliations of maximal Kodara dimension on projective surfaces have finite group of birational transformations. So I want to talk first about, quite quickly, about the result which generalizes this last result of Pereira and Sanchez. So we can show that this time on a variety of any dimension, and for a foliation of any codimension, a general type foliation with canonical singularities on a normal projective variety has only finitely many birational automorphisms. So this is exactly the same result as Pereira and Sanchez, but in any codimension and for foliations and for varieties of any dimension. We have this hypothesis on singularities, nonetheless. The result is actually a bit more precise. We can treat the case of foliations of a joint general type. So with some definition of epsilon canonical singularities, it is enough for kf plus a small, well, a positive multiple of kx over f to be big. And then again, the group of birational automorphisms is finite. I'm not going to give all the definitions in this page because I want to concentrate more on an analog. So on the second question, actually, which I pose here. So on the transverse section. And I'm going to talk about transverse homogeneous structures, which are it's the kind of foliations that we'll treat in what follows. So from now on, suppose that the codimension of f is equal to 1. And I'm going to give you an intuition of what a transverse homogeneous structure for f is. So it's somehow a foliated analogous of a principal GX structure. Recall, or I'll tell you that in a GX structure, we have a model manifold X, which is homogeneous with the action of a group G. And another manifold M has a GX structure if it has some special charts with values in X, such that the changes of charts can extend to elements of G. So locally, it is modeled over X, and these models are uniquely defined up to elements of G. So for foliation, how can we generalize this notion? So you know that a foliation, at least around regular points, is defined by first integrals. And we can take locally for the Euclidean topology, first integrals with values in a special homogeneous variety. So in this case, a homogeneous variety of dimension 1, a complex curve. Plus, I said these compatibility conditions, meaning that the transition functions should be special. So they should be in this group of transformations which make the variety homogeneous. To give some more concrete examples, the structures we'll actually be interested in are the following. So the projective structure, or a projective structure to be more precise. So it will be first integrals with values in P1, which is our model manifold for the space of leaves somehow, and transition functions in PGL2 of C, so just transformations of P1. This can be specialized, so first maybe to an affine structure, so first integrals with values in C, transition functions which are affine transformations, or to some constant curvature metrics. So hyperbolic, additive, and spherical structures, they say that first integrals, that we can find first integrals with values in the disk or in C or in P1, and transition functions in PSL2 of R or C or PSU2 of C. So this means that we have transverse metrics with constant curvature -1 in this case, constant curvature 0 in this case, and constant curvature +1 in this case. Okay, so this was to give you an intuition of what you should think about when we talk about transverse homogeneous structures. Actually, what we consider is more generally degenerate structures. So this description with first integrals is valid outside some hypersurface H, which turns out to be F invariant. And we also need to impose some conditions on the behavior of degeneracies around H. So the actual definitions of all these structures with the degeneracies are a bit more involved, and I won't talk about them here. So on to the statements. So we consider a projective manifolds and F a foliation of codimension 1, which is supposed to be transversely projective. So the first statement is an alternative. Basically, it says that if the transverse section of the group of birational transformations is infinite, meaning that it mixes the space of leaves in an infinite fashion, then F is actually virtually transversely additive. What does this mean? Additive, recall, is a special kind of projective transverse structure. That means that we can actually find an additive structure on top of having a projective structure. And this virtually means that this is true up to passing to a variety X prime, which is generically finite over X. In fact, it turns out that this being transversely additive in the degenerate case means exactly that F, always up to passing to a cover, is defined by a closed meromorphic one form. But in the case of hyperbolic structures, the result can actually be made more precise. So recall that hyperbolic structures are a special type of projective structures. In this case, then we can't actually have an infinite transverse section of Beer X of F. And furthermore, we can show a hyperbolicity property, namely that any entire curve, so any holomorphic map from the complex plane to X, is not Zariski dense. This should not be so surprising because, so I didn't talk about it earlier, but how should we think about, why do we ask what's the action on the leaves like, and how should we think about it? I talk about the space of leaves. So this is usually a nasty object, but there is one special case where this object is kind of nice, and it is the case of algebraically integrable foliations. So in this case, the foliation is just defined. The leaves of the foliations are just the fibers of a rational map, and the space of leaves can be identified with the image of this rational map. So this is exactly the same property that we would expect if the foliation was defined, so that we can trivially verify if the foliation is defined as a fibration onto a curve of higher genus. Because in this case, on the base, we have a natural hyperbolic structure, which is just defined by the usual description of the curve as a quotient of D. And the transverse section of Beer XF identifies with a subgroup of the automorphisms of the curve. And we know that this group of automorphisms is finite. And we also know that entire curves, the image of entire curves in higher genus Riemann surfaces are just points. So entire curves should be contained in the fibers of this fibration. And this is exactly a foliated analogous of this property. Okay, so I should have a couple minutes left. I want to go quickly through some elements of the proof. To keep things simple, I'll just treat the hyperbolic non-degenerate case. So this shows already a good deal of the ideas for the proof of the other result. So non-degenerate means that the structure is everywhere defined. Let's say that it is defined as locally special first integrals I talked about. So the first idea is to consider the monodromy associated to the structure. This monodromy, how do we construct it? So we have these special first integrals. The idea which we could start with is to try to make them global. So we try to take nearby first integrals and change them so that by element of PSL2 of R, so that they agree on the intersection, and try to globalize the first integrals that we are given. The problem is that once we go back to the initial point through a loop, something might have changed, namely an element of PSL2 of R might be the difference between the first integral we started with and the one we find after walking through the loop. And this is exactly what's the problem on defining a global first integral. So this monodromy encodes how far we are from having a global first integral. This global first integral will actually be defined on the universal cover of X. So in this case, we have in general this monodromy representation, and we can show that the image of rho is actually Zariski dense in PSL2 of R. Now we can use a result of Corlett and Simpson, which just talks about actually representations of fundamental groups of quasi-projective varieties. This result says, in this case, says basically that rho factors through a map onto this variety H, which is a quotient of a polydisk, which we call a Shimura modular orbifold. What does it mean that rho factors? Well, on H we have another representation of P1 of pi 1 of this into PSL2 of R, which is given by the monodromy of one of the modular foliations, which are the foliations defined by the coordinates on the n. And the fact that rho factors means exactly that. So we can start from pi 1 of X, go to pi 1 of H through psi star, psi lower star, and then go to PSL2 of R through this monodromy. And we obtain the same thing as going directly through rho. Now to go on, we remark that we can use some uniqueness properties of transverse structures, at least in the non-algebraically integrable case, which is kind of easy to treat. And this shows basically that this factorization is essentially unique, that we can find an induced action on the image of psi. We can show more. We can show that F is actually the pullback of one of the foliations on H. So actually, to show the finiteness of the transverse action, we can just show it on the base B. And we do show something more. Actually, we show that the action on B is finite itself. Is actually finite, not just transversely finite. And this follows from, so we know rather well the geometry of objects like this. We know that all algebraic subvarieties of H are of like general type. And from that, adding the foliation and all we know about the dynamics, it's kind of easy. So it's the last passage to show that the action on B is actually finite. So the action on B is finite, means that the action on upstairs, essentially on X, had to be transversely finite. And this finishes the proof. I hope it wasn't too messy, so this is the end. Thanks for paying attention.
Thank you, Federico. Are there questions or comments?
Yes, I would like to ask, so these transversely hyperbolic foliations, do you have some criteria for transverse in terms of the conormal bundle or something?
Yes, we have. So let me just recall. Essentially, if the conormal bundle is pseudo-effective, was that the criterion? So Touze showed that if the conormal bundle is pseudo-effective, then we have a transverse hyperbolic, well, non-trivial, let's say.
Mm-hmm.
Then we have a transverse hyperbolic structure.
And in the other direction, if you have a transversely hyperbolic structure?
There was some issue, as I recall. It wasn't completely... I should look at it again, but I think there was some issue to prove the following, the converse statement.
No, I think if you allow, you have to allow logarithmic to look at the logarithmic conormal bundle with poles on the degeneracy locus of the structure. Then you do have that the thing is pseudo-effective, and if the structure is not trivial, I mean not algebraically integrable, you also have that it's pseudo-effective and Kodaira dimension, this logarithmic canonical bundle is pseudo-effective and of negative Kodaira dimension. So this is the results of Fred Touze. And he explains part of that, at least not the logarithmic version, but the version for without the degeneracy loci is explained in his mini course in detail.
Okay, thank you.